Hello everyone and welcome to this tutorial. You will learn today about entity summarization in knowledge graphs, about algorithms, evaluation methods, and various applications. This is a joint presentation by three people: Gong Cheng from the University of Nanjing in China, Kalpa Gunaratna from Samsung Research America in the US, and by Evgeny Kharlamov from Bosch Center for Artificial Intelligence in Germany and University of Oslo in Norway. If you have any questions, comments, would like to get in touch with us, please feel free to drop us a line using the emails which you can see on the screen. This tutorial is 2.5 hours, and we split it in 6 parts. In the first part, you will learn about knowledge graphs, who are they, why entity summarizations are important and useful for them. This will be given by me. The second part will be presented by Kalpa. He will dive into technical features of entity summarizations and focus first on generic and then on specific features. In the third part, Gong will present frameworks how to combine various features and discuss some representative algorithms. In the fourth part, Gong will dive into evaluation methods and discuss evaluation results. In the fifth part, I will be presenting entity summarization with users' feedback. And in the sixth part, I will conclude and discuss future directions. Enjoy this tutorial. Part 1. Introduction to knowledge graphs and entity summarization. What is a knowledge graph? It's a format to represent information where nodes are either entities like USA, Tupola, Elvis Presley, Priscilla Presley, or classes like singer, person, actor, entity. And directed edges either connect entities, so they're properties of entities. Elvis Presley born in Tupola, Tupola is located in the US, Elvis is married to Priscilla, and vice versa. Edges also represent typing of entities, so Elvis Presley is of type singer, Priscilla is of type actor. Edges also help to form class hierarchies, so the singer is a subclass of person, actor is a subclass of person, and person is the subclass of entity. This format is actually quite popular nowadays, and in many domains, people use knowledge graphs to represent information. In media, BBC used knowledge graphs to store information about Olympics 2012, about Football World Cup 2010. A lot of geographical data is available as knowledge graphs. For example, Ordnance Survey does so. A lot of public governmental data is in knowledge graphs. In the UK, at least, this is an example. In industry, companies have their corporate knowledge graphs to store information, and there are lots of knowledge graphs available on the web. I will go now through several examples, explain how knowledge graphs are used in those examples, and then motivate the necessity of entity summaries. Able is a company that provides services in the oil and gas and offshore wind industries, and in particular, it produces oil platforms that look like that. Able has a knowledge graph called MMD, which stores information about many things, including catalogs of components that Able can use to produce oil platforms, compatibilities between components, also national and international standards behind manufacturing of oil platforms, ISO standards, environmental standards. And this knowledge graph is used for various reasons. In particular, it's used to support 3D design of oil platforms, and those 3D designs are later on used for the actual manufacturing. In this case, the knowledge graph helps in optimizing weight control, logistics, and so on. How can entity summaries be useful for this very example? Well, an entity inside the Able knowledge graph, for example, a pump, can be compatible with hundreds of other entities. And a summary could be quite useful. It can help in getting a better overview of knowledge graph components. The next example is Festo. Festo provides solutions for factory automation, in particular drivetrains that help to move things in factories. Drivetrains are composed from basic components like axes, motors, controllers, and there are thousands of them available at Festo that can be combined in millions of drivetrains, which in turn can be combined further in complex Cartesian systems, and there are billions of combinations of base components in them. Festo knowledge graph encodes basic components, characteristics of those components, compatibilities between them, and then also it is used for various applications, including, for example, visual design of complex Cartesian systems. How can entity summaries be useful in this application? Well, in the Festo knowledge graph, a train can be compatible with hundreds of basic elements and other trains. In this case, a good summary can help in finding the most relevant compatibilities for a given basic component or a drivetrain. Another example is from Bosch. Bosch is a large manufacturing company producing various things from automotive to house appliances. And in its productions, Bosch uses various materials. It produces materials, purchases materials. And Bosch, in order to handle material information, Bosch has a material science knowledge graph, which is constructed from a large corpus of textual documents, and it contains information about chemical experiments, chemical materials, like that one, and devices to run experiments. This knowledge graph helps in analyzing experiments and in purchasing better materials and so on. How can summaries be useful in this application? A complex chemical experiment and actually can involve dozens of materials, devices, and can have multiple conditions. A good summary can help in better visualizing the most important characteristics of an experiment when the user is browsing a knowledge graph. The next example is from the web. Knowledge graphs, and here there are two things I'd like to say. Knowledge graphs are available on the web, and one can actually find and download quite many knowledge graphs. In 2019, there were more than 1,000 knowledge graphs interconnected between each other, and this is known as linked data cloud. So here you can see this linked data cloud, lots of circles which are knowledge graphs, and they're interconnected. They cover various domains, and here different colors depict different domains, and they are huge. Jointly, this whole network of knowledge graphs is huge, but actually individual nodes are also large. DBpedia has 9.5 billion triples. DBpedia is a knowledge graph version of Wikipedia. Besides separate data sets, knowledge graphs on the web, one can find a lot of knowledge graphs scattered across HTML pages or embedded in HTML pages. In 2019, people behind the Web Data Commons initiative did an extensive crawl of the web and checked how many triples or edges from knowledge graphs are embedded in HTML pages. And it turns out that there are more than 31 billion triples scattered across HTML pages. They correspond to about 14.5 billion entities, and about 37% of HTML pages they crawled contain some bits and pieces of knowledge graphs. So knowledge graphs are available as datasets or scattered across web pages, and summaries of knowledge graphs, and in particular summaries of entities, could be of great help to make knowledge graphs more digestible for both machines and humans. The next example is from BBC. In 2010, during the World Cup, Football World Cup, BBC had a knowledge graph that contains information about teams, groups, players, and then the BBC web pages about World Cup, they were constructed automatically from this knowledge graph. So this is called dynamic semantic publishing. More than 100 pages are offered by BBC as those in dynamic semantic publishing. The same was done during the Olympics 2012. Web pages of the Olympic Games were constructed from knowledge graph. How can entity summaries be useful in this application? Here the situation is that a page on a BBC portal has a limited space and all the important things can go in it. At the same time, knowledge graphs have a lot of information about individual teams. So a good summary can help in selecting the most relevant, the most prominent information to be presented on the web page. The next example is Google Knowledge Graph, which is probably the most well-known knowledge graph nowadays, and many of you already saw this knowledge graph in action. When you do search, for example, when you look for Norway, then what you get is the search result, you get web pages, and also you get property value pairs computed by Google from its knowledge graph. An example of property value pairs is here. So the population of 5.4 million people is the population of Norway. Also, capital city Oslo, it's another property value pair for Norway. And when the web pages are retrieved by Google, they are presented as snippets which are enhanced with these property value pairs. So in this snippet for Wikipedia page of Norway, there are a few property value pairs embedded in the snippet, or those property value pairs could be aggregated in summaries like you see in this box. This is actually a summary. So Google already uses summaries to represent search results, and since there are a lot of property value pairs in Google Knowledge Graph for Norway, for other things that one is looking for, Google has to come up with some smart ways of selecting the best property value pairs describing an entity and then depicting them, presenting them in a limited box available for the summary. To sum up, summarizations for knowledge graphs are actually needed and quite important in many industrial and web applications. They're needed for both machines and users, and there is no unique way of doing so. There are many ways one can summarize a knowledge graph. One can summarize the knowledge graph around its entities, around its edges, to summarize various fragments of knowledge graphs. And one particular and important type of entities, knowledge graph summaries, which is widely studied, is summarization of entities. In the classical way, entity summarization is a set of very important property value pairs relevant to this entity. But more generally, one can summarize an entity by looking at the neighborhoods of this entity and say picking entities, other entities located in this neighborhood, entities which are not that far from the one which is to be summarized. One can aggregate neighborhoods in different ways. In this particular tutorial, we will focus on the classical way of entity summarization, where the summary is a collection of property value pairs for the given entity. More formally, given a knowledge graph T and an entity E in it, we define the description of an entity, which is denoted as desc E, and it is the set of all edges that either point to E or point from E. Given this description, one can now formalize the notion of a summary. A summary is a subset of the description. Typically, people consider size-bounded subsets, and that way there is a summary of size K, which is a subset with the size at most K. Now, there are many possible subsets of size at most K available for a given entity, And the question is, which is the best one? And here we come with the problem definition. The entity summarization problem is the problem of finding a subset which maximizes some notion of quality. So we assume that we are given a scoring function, score, that can assess the quality of subgraphs in T. It maps subgraphs into positive rational numbers. In this case, the entity summarization problem is to find the subset of the description of E that maximizes this score function. In the next part of the talk, the tutorial, Kalpa will tell you a lot of technical, interesting details about the ways to find these score optimizing subsets S.
Thanks, Evgeny. Hi all, this is Kalpa. So I'll be going over with you the next two sections, and I'll be talking about and explaining the existing systems and approaches that use generic technical features, that what are the different ways of capturing different features for them to make meaningful and high quality entity summaries. And then next, briefly, we'll discuss and look at how different approaches have used specific technical features, meaning for certain domain-specific applications, and then situations they have used different ways of extracting features that are very specific. So these two sections I'll be going over and then briefly presenting you in regards to existing systems. And as you have already have come across the descriptions and the introduction that Evgeny already gave, covering some introduction to edit summarization and then how things work, what does it mean. But let me start with giving you a little overview and a running example, and then we will use that to understand how these things work. So let's start. So the first part, we'll go over the technical features. So here we will look at running example, a part of knowledge graph, a snippet. You can see there are various entities on the right hand side here, and there are actually 8 entities, and then they are linked with various relationships. So on the left top corner that we see a triple is going to be formed using 3 parts, basically: entity, property, and then the object part. So object part can be a class, literal, or another entity. So basically that's the outline, how a triple will look like. And then an entity description, basically a collection of triples that describes that entity using other entities, literals, and classes. So we'll also pay some attention to some notation here. If you could see this table, basically a property of a triple, we describe an instance of a class, meaning an entity belongs to a class, that meaning the instance of inst within parentheses C means instance of a class, that means an entity referring to an entity of specific class. Global frequency, and then we have type specific frequency, that means frequency measured for a certain type. And then we have class level frequency, and then we also look at like local frequency, and then property value frequency, And also down the road, we look at like measuring similarity of the certain values, property values. We will come across discrete similarity, that is binary, true or false, and a numeric similarity, how to measure similarity of numerical values. So let's start. So we'll treat this. On the right hand side, we have this small subset of entities and relations, a subgraph representing a smaller knowledge graph. So it will help us to understand different features and how they look like. So basically looking at features, technical features, we can categorize them to three main categories. First, we look at frequency and centrality, basically meaning the more they appear, they are considered important and useful. And then informativeness, that means sometimes less frequently appearing things may be important for entity summary. And then the next category of the specific technical features are diversity and coverage. That meaning we should not select similar facts to an entity summary, because then it will be boring and they're not useful, and then won't make any sense to a human or even a machine. So frequency and centrality, the first category we look at, and then that we can break it down into 6 different ways of measuring these features. So frequency of property, and then you can look at then frequency of the property value. And then instead of measuring the frequency, you can measure the importance or the graph-based importance using centrality measures and property value. And then centrality measure of a triple, that means property and value together. You can make like centrality means, for example, page rank kind of graph search algorithms, random surfer-based algorithms, and then LDA, and then formal concept analysis people have done. So these are basically the breakdown of existing systems, how different features they use. So let's go in and then see. So basically, we look at the first one, see what it means, like frequency of a property. Basically, frequency of a property also we can measure using different ways of calculating this value. For example, global means we measure the frequency of a property by calculating all entity descriptions in the data set, and then how frequent that property appears. So if you look at, and then again, we can measure them using entity level, and then also triple level. That means we can measure inside each entity description and then count the properties, how many times they appear, or we can look at and we can look to count the number of triples that appear in the data set. So let's take an example. Yeah. So if you look at, if you are calculating using entities, just counting entities, in this example, you can select works at is going to be ranked higher than directs relation. So why it happens is, like, if you look at the number of times that this property appears in an entity description, works at appears here. Let's see here, 1, 2, 3, 3 times, and then directs appear only once. So there are 3 times the works that appear. So if you just count the entities that have this property, then it's going to be ranked higher than the directs property because it appears only once. And then if you are going to count at the triple level, so if you take example knows and works at, and knows, we get the count as 5, and then works at count as 3, because how many triples that actually appear with this property. For knows, it has it's appearing in 5 times. You can see 5 times, and then works at appears 3 times. So for example, yeah, you count all the triples, not entity description. Sometimes a person can have 2 properties linking to 2 different property values, but then if you're counting the number of triples, you will be counting the triple count as 2 separate counts rather than counting as one, like in an entity description. So this is 2 different ways of calculating the global frequency of a property. And then let's look at, so you can always compute frequency of a property using counting the different types. So number of entity descriptions of a specific type that has this property. So it's described here. And then you can also count the frequency of a property using counting the number of different classes that this property appears. So if you look at our smaller graph example, again, if we take the relation work set, and work set appears in in total it appears 3 times, so it has 3 triples. But then if you look, it appears in 2 different classes, person and then professor. So if you count the class level, it will be only 2 instead of the other values that we looked earlier, because the entity that originates this property, and then we only look at its assigned how many different number of classes that we can get by analyzing all the types that each of these entities belong to. And then we can always look at counting frequency of a property locally to each entity. So if we look at the example again, we take 2 properties, knows and then works at, and then knows will be ranked higher than works at because knows appears more than works at. And then for the entity Q, the person named Q, if you look at the graph, knows from Q it goes Q knows Jia, and then Q knows Sang, and then Q works at Websoft. So Q has two nodes relations outgoing to two different entities, and then it has only one works at connecting to Websoft entity. So in the local rank, it means like inside Q, for Q, it has two count for nodes, but then one count for works at. So works at will be ranked higher. Nodes will be ranked higher than works at, and then we can see by using these different ways of counting approaches, we get different values. Even for the same property, we use global frequency of a property, we get a different count. Local, we get a different count. So different systems use different ways of calculating these values. So let's go on to the next type of the feature. So we looked at how to count the properties, and then how to get a value for property, the frequency. Now systems also are interested in measuring the frequency of property values, because same as treating frequency of a property value is also maybe important for a system. So when measuring the frequency of a property value, you can also measure again at the entity level and then the triple level. First, we list if it is entity level, we calculate the number of subject entities that the value appears as the value appears in their description. So different subject entities for property value. And then if we are counting this feature as a triple level, we can calculate number of triples that this value appears. So if, for example, if the same entity has using two different relations linking the same value, so if we are measuring the triple level, it will be counted as 2. But then if we are measuring at the entity level, even though you have two triples, but then you only have one subject connecting to two property values using two different the same two property values using two different properties, but then the same subject we get 1. So that's the main difference. So you can calculate in different ways. So if we look at again, let's look at a specific example. So Jia, if you take the entity Jia appears 3 times as a property value, where for Sang appears 2 times in the entity description. So if we count entity level, Jia gets 3, and then Sang gets 2. If you see in the graph, yeah, and then if you measure at the triple level, we can take the example Websoft and Jia. Websoft and Jia, again, Websoft appears GIA appears 3 times as the value, but then WebSoft appears 4 times. So WebSoft gets count 4 because it appears in 4 different triples. So we even, for example, if we, for example, for WebSoft, if we you look at the links that coming from Q to WebSoft, Q works at WebSoft, Q directs WebSoft. So if we are measuring at the entity level, so both the property instances or the triples that are connecting Q and WebSoft using works at directs will be counted as one for WebSoft because it has only 2 items coming from one entity Q, but then since we are measuring now at the triple level, they can be counted as 2 different triples. So that's why WebSoft gets number 4 if we count using triple level, but GR gets 3. So if we use the triple level, WebSoft can be ranked higher than GR because we count 4 different triples. So this is actually how to compute property and value frequency. Next, we look at the centrality, how to measure the centrality of a property value. So basically, if you think knowledge graph is a graph, so one could think we can run graph-based centrality measure, which is natural to think about PageRank. So yeah, people have tried using PageRank and also then modify to weighted PageRank. So if you are using normal or traditional PageRank, the assumption that PageRank makes is that each edge is treated equally because it's connections in a graph and then the used to make PageRank normally it has the same weight. So, but in a knowledge graph, you can think maybe different edge or the relation carries different information or importance or different ways we want to measure. So rather than using default or generic PageRank, we can use weighted PageRank. So certain properties will get certain value over the other because they are not the same. 2 properties may not be the same because they mean 2 different things. So we can run PageRank or weighted PageRank. And then another variation of, we looked earlier like centrality of a property value. That means take the value and then represent them as nodes in a graph and then run PageRank similar to a web page. That's only taking the value because to run PageRank, you need nodes and then their connections. But then how about considering the entire triple and then try to come up with a ranking mechanism using centrality measures? So this interesting modification has been also tried. So you take the property and value together. So take the entire triple and then represent them as in a graph and then run PageRank. So put whole triples as nodes instead of only values. And then if you put all the triples as nodes, and then how normally a triple is not connecting to another. So we cannot think of that because triple is the format or the structure that makes the graph connecting nodes using edges to another node. So Now, if you put whole triple into a graph representation, now they are not connected. So you can think of connecting them as measuring similarity between triples, so they have now connection. Then you can run page rank kind of centrality measure. So that way of modification allows you to represent the triples into the graph representation. Now then you run the centrality measures of page rank algorithm. Now it's possible to run. And then modification of this into topic coherence. That means now you have the centrality measure, but then now adapt it to link and take into consideration another query or some input that needs to be matched. Now let's look at the last set of features on this section. So people have used also LDA and FCA, latent digit allocation, and then technique, and then formal concept analysis. So in LDA, properties are considered as topics, and in each property is distributed over all the property values. So then you take these LDA techniques and then use them to rank or get the features. And then in formal concept analysis, you try to put in properties and values into a hierarchy. Then you kind of measure the elements depth in the hierarchy, and then using this formal concept analysis, and then come up with these features to make up entity summary. So in we can see in FCA, and then basically we think like it gives preference to infrequent properties and then frequent property values in. So if you look deeply, we think that's what happens if we use formal concept analysis. And then also just shown like more recent papers use these kind of techniques, and then latent direct allocation, and then FCA, formal concept analysis, seem to be kind of different features that people try to use over what we have seen earlier. So next we'll talk about informative. We saw now the frequency aspect. Now we look at the informativeness. So informativeness can be divided into statistical and ontological. So in statistical informativeness, what does it mean is like, instead of measuring frequency or popularity, property and value separately, this approach looks at them like if property and value together, so the value alone can appear many times, or it can be frequent, or it can be popular, but then property alone can appear many times. But then if you combine both as property and value pair in a triple, now if it appears less frequently, then we should be thinking it is an important thing to consider in an entity summary, because property and value together can mean something unique. And then if it is less frequent, that means it is important to consider it into entity summary. So if you look at using our example, so a property value pair works at, and WebSoft has this value minus log 3/8, whereas the direct and WebSoft property value pair has this minus log 1/8. So we see like rather than person works at WebSoft, if somebody is a director at WebSoft, that's less frequent and also may be important. So direct web, so inherently gets higher rank here because it's together property value pair appearing less frequently. So we see intuitively it is also the case. And then also that statistical way of measuring informativeness. And then in ontological way also we can measure, like we get the property type normally used to assign an entity to a class. And then we can measure like different now entities assigned to these classes, and then these classes have like in ontology hierarchy. So based on where the class appears in the hierarchy at the top or lower level, so based on that we can measure some informativeness. So for example, deeper class has more specific meaning and information, and then maybe it's more informative. So let's look at the next set of features, and then diversity and coverage. So we looked at so far frequency or popularity and informativeness or importance. But if we think if we are only going to consider how frequent they are, how important or frequent, less frequent, saliency, all these things. But if you think, if we only use those ranking mechanisms and then try to rank facts, and then based on this ranking, we try to select a summary for an entry description, it could happen like more often. You might select same type or same or very similar facts into a summary because you are not paying attention whether you are selecting the same type or same kind or very similar facts. Because a summary is short, inherently we are selecting something very short from a large collection. If we, because of the fact that they ranked higher and then you just select them, it could turn out like they all mean very similar things. So then you end up saying redundant things in your short space that you're given to make the summary. So finally end up making useless and then meaningless summaries. So together with considering all these features, we should also try to make summaries that are meaningful. So how can we make it? So we have to add one more dimension, one more type of feature. It's like we should be selecting diverse facts as possible, because as many diverse facts as possible, because then we would be giving more overall picture of the entity and also good ranking from these diverse facts. So that's the main idea, like we should also be considering diversity. So measuring diversity, we see so we can measure diversity using different techniques. So very naive and then straightforward approach is like using discrete. That means you can measure property or value, and then if you are going to select the same property again, we can say like you are discouraging that selection, or you're not going to select it, or penalize or not select it. So basically using discrete similarity. So you have binary value 0 or 1. Either if you already have selected the same thing previously, you're not going to select it again. So the next type of diversity, or the way of measure diversity and coverage, is like using some textual measurement. So for example, you can do edit distance. That means given, let's say, you get the property or property value and then see using textual edit distance measures how similar they are or how dissimilar they are. For example, you can take WebSoft, the string WebSoft and director of WebSoft. They can be considered as similar because they have some overlap and then basically using edit distance. And then another way of measuring textual diversity or in a sense similarity is you get the bag of words for each property or property value, and then you are going to measure the overlap. So higher the overlap, they are similar, so you should not be selecting them. For example, WebSoft and director WebSoft again is going to be similar because if you just split them into words, they have a clear overlap. And then the other way of measuring diversity is for semantic diversity and coverage. Basically, they are for numeric and logical. For example, we need to have a way of measuring how two numeric values are going to be different or similar. In this technique, they introduced to measure numeric similarity given two values, numbers. If they are the same, you give 1. If they are not the same, and then both of them are positive or 0, or one of them are 0, you get -1, -1, and then if they are not equal and then they are also positive, then you measure using their fraction, like get the minimum and maximum and then get that fraction. So it turned out to be a reasonable way of measuring the numeric similarity. Then we also have, we can also use the logical similarity or dissimilarity to measure diversity. So basically we are saying we can use class level overlap or reasoning of two property values. For example, if we take two triples, Q type professor and again Q type person, they are going to be redundant because we know from the ontology professor and person are linked, and then actually professor is subclass of person, so they are really related, so they are going to be similar. So selecting professor and person, those two triples may not improve diversity, but actually negatively affect diversity and then affect coverage. That means you will have less coverage of facts because you are telling the same thing, similar thing, redundant facts. So we have looked at different ways of computing these technical features. So if we put them all together, we have this breakdown. So we have generic features. We looked at basically they can be categorized into 3 different items: frequency and centrality, informativeness, and diversity. So frequency and centrality means like you are mainly focused on computing frequency, how frequent they appear, how popular they are, and informativeness means, or informative means, if some fact appears less frequent, then it should be important. So property and value together, we are considering property and value together. And then diversity and coverage means like we should also be considering some features to measure this aspect. So, so that when we create an entity summary, we give an overall picture of the entity and giving also consideration to ranking using information and frequency, but then diversity brings in, you discuss or you present different facts representing different parts of the entity description that turn out that the quality of the entity summary goes high up, because you're not saying to the user or the machine, whoever uses this entity summary, the same thing over and over again, because you also have very short space to fill in from a large fact set. So this is the breakdown of generic technical features. Next, we can look at briefly about specific technical features that people use in specific domains or applications. So that's why they are called specific features. They are very specific to a domain or application. So let's go over to that section. Okay, let's look at specific technical features. So these features are the ones applied in various approaches, maybe using external information, like using external knowledge bases, knowledge, or very specific to certain applications or use cases. So we identify main three such types of features. One is domain knowledge, one is context awareness, and the other is personalization. So domain knowledge is about you try to use some domain specific information that cannot be applied as in general sense. And then context awareness means in your application, you can take into account the additional context information on top of the features that we discussed earlier. And personalization is basically you want to personalize your application to the specific application. So for using domain knowledge, certain applications have used domain-specific information. For example, using movie ratings to make summaries and or rank movies, so you can rate the movie ratings to decide which movies or actor gets higher rating, so you can make use of them. And also the other approach, they make use of certain values that you can get out of in this place and event. For specifically in those entities, you can make your entities look better because you have this specific information coming from this domain. And then people have also used external knowledge bases like Wikipedia. So for example, using Wikipedia page structure or internal linking structure to get and measure the importance of entities, and then using running page rank, using backlinks, and then interconnections. And then in LDA, people have used entity categories to enrich the LDA distribution and then compute better entity summaries. And then people also have used Wikipedia page categories, and then to rank better ranked entities, and then make better entity summaries. And then next we can look at context awareness, which is also important for certain applications. For example, we can see some examples here. When you are making entity summaries, let's say a user is giving some input or query, or there is a query, so that you can make use of that information and make up an entity summary. So the information or search intent or user intent is captured in somewhat in that user query. So you can process that and then try to make up your entity summary aligning to what information is present in this query. For example, if you take the triple Q directs WebSoft, will be going to be similar to a query if the user input something like researchers at WebSoft. So if you are making an entry summary for WebSoft or for Q, maybe you should be showing WebSoft that relation. And then again, extending this line of work, and you can also make like query sessions and then make that countable in one query session. And then also when you're making entry summaries in document browsing or assisting users trying to understand what this document means, and then other entities present in this document, how are you going to comprehend or get an understanding of the document using entity summaries? Then for that purpose and for that application, if you're making entity summaries, you can make use of contextual information present in words and other tokens in the document, and then you can select fact for each entity that you're making summaries that are appearing in this document using this context information. So you can align the selected facts in the summary to this information or context information in the document. And also another important or aspect is entity interdependence. A use case like you are making an entity summary not for one at a time, but you're going to make entity summaries as a collection of entities. So you have more than one entity to make entity summaries, then as a collective effort, you're making entity summaries, then you have to look at all the other entities also at the same time and then make the entity summary. So your context awareness is performed or achieved by also paying attention to other entities in the set that you're making summaries collectively. And then personalization is also important. You can think of making entity summaries to each user's preference. So one way or four people have come up with techniques like based on user clicks on a web search history or some way of user clicks, you can get the likes of a user and what are his preferences, and then make up entity summaries. So if you look at as a broader picture, like specific features, you have domain knowledge using knowledge bases, then context awareness, you have query relevance, and then document context using word and more natural language level, and then entity interdependence. So you're making a use case like creating entity summaries as a collection, not one by one. And then personalization. So these are very application specific or domain specific features that you come across in entity summarization. So this brings us to the end of discussion on these different types and kinds of features. Next, my friend Gong will go over like different frameworks and how to evaluate entity summaries. and then more interesting stuff is going to follow. Please stay tuned.
Hi, this is Gong from Nanjing University, China. Kappa has introduced a lot of generic and specific technical features for entity summarization. Now I will show how to combine multiple features into a full entity summarization system, because for many applications one single feature does not work quite well, so we typically need to combine multiple features. And during this introduction, I will also illustrate with several representative algorithms for entity summarization. So in the following, you will know how to combine multiple features, and also you will see some typical solutions to entity summarization. Well, basically, we divided the existing frameworks into 6 types for combining multiple features in different ways. So we will firstly look at some simple frameworks, and then we move to a random suffer model. These 2 models are basically very simple and maybe not very effective. So next we will look at some similarity-based grouping, and also MMR-like re-ranking, and then some more complex combinatorial optimization models, and finally learning to rank, particularly deep learning. Well, as you can see, if we look at the first 5 frameworks, they are typically unsupervised. This is not surprising because most of the current systems for entity summarization are unsupervised. And in the last, we will have a look at some supervised systems, including some very recent deep learning-based methods. So firstly, some very simple frameworks. For example, if in your system, you need to consider 2 features. For example, you have 2 rankers for ranking triples. First is the ranker A, and second is the ranker B. For example, ranker A is for popularity, or ranker B is for, I don't know, maybe for informativeness. And so the most simple way is that you can select Z triples from ranker A and select K minus Z triples from ranker B. So you will have a total of K triples as your output. This is very simple, but you need to define Z. And anyway, this kind of very simple framework that has been adopted by some system. Probably more effective method is that you can do some, if you want to combine multiple features, you can multiply their ranking scores, or you can calculate the sum of their ranking scores. For example, if here is a famous system called LinkSum, published at ICWE conference by Zahama. So in this system, well, we know that in a triple, basically we have a property and a value describing an entity, right? So we need to rank properties, and we need to also rank values. So for ranking properties in this framework, in LinkSum system, it computes the product of 3 elements. First is the frequency of the property. The second is the exclusivity of the property. Exclusivity basically it means that is inverse to the local frequency of a property. I mean, if a property is locally frequent, I mean, it has a lot of values for the same entity, then this property is not very exclusive. Well, description means that, a property is defined in an ontology, and a property can have one or several human readable names. It can have more than one domains and ranges. So basically, if a property has many of such description triples, I mean, it's actually ontological level triples describing the property itself, then it could be a very important property because its description is very rich. Anyway, so you can compute the product of 3 or even more factors about the property for ranking this property. And for the values in this system, they compute a linear combination of two ranking scores. First is the page rank of the value in the graph, and second in the knowledge graph, and the second is backlink. What is a backlink? For an entity, it may be described by a property value, which could also be an entity. So we have two entities here, and these two entities may have their own Wikipedia pages. And if these two Wikipedia pages link to each other, okay, so we know that this property value could be a very important property value for this entity because they link to each other. That's called a backlink. So for value ranking, we compute a linear combination. So we actually calculate the sum of these two scores. So in link sum, for property ranking, they compute the product, and for value ranking, they compute a linear combination. Well, it's still very simple framework. So these frameworks are very simple, which is good because it can be easily understood and you can easily tune the parameters. For example, you can change the alpha here very easily. Well, the downside is that these simple frameworks can't represent diversity and coverage. So basically, it's just, compute some ranking score, compute some combined ranking score for each triple, and then you just choose top ranked triples. But the problem is that top ranked triples may not comprise the best summary. Okay, because you can't naturally model diversity and coverage in these simple frameworks. So now we move to some more complex models. A random sample model. Random sample model was actually developed by myself and other colleagues. It's in an early work. This system, we call it rallying. We call it rallying. In this rallying system, we construct a complete graph of triples. So in this graph, it is a complete graph. So you have edges between every pair of nodes, but here a node is a triple. Okay, a node is triple. So it's a graph of triples. And we consider a suffer that does some kind of random work in this graph. Just like in PageRank, so the suffer can have two types of actions. First is the suffer can move from one node to another along an edge, right? And the second type of action is that the suffer can randomly jump from one node to an arbitrary node. So for move here, the suffer can move to different nodes along different edges with different probabilities. How can we compute these probabilities of moving? We compute the relatedness between two triples. So if the two triples are closely related to each other, then we believe that, okay, the suffer has a higher probability of moving from one of these two triples to the other. And for jump, I mean, for the random jump, so how likely the suffer will jump to an arbitrary target triple? So we believe that the probability is related to how much information the suffer can gain from this jump action. So if the target triple can provide a lot of information, then the probability of this jumping action is higher. So we call it a relational move and informational jump. So here, let's look at some math. So basically, it's someone may be very familiar with this formula because it's actually an iterative computation of PageRank. So here M means move, relational move, and J means jump, informational jump. So how we compute the relatedness between two triples? We compute their relatedness between their properties and between their values. Well, so property, for both property and value, we take their string forms, I mean their names, for example. Then we compute their PMI, pointwise mutual information. So basically we submit these two strings to a search engine like Google, and then we look at how many results are returned for these two strings collectively and also separately, so that we can know their relatedness to each other. And for the probability of jumping to a target triple, we compute the self-information of the target triple. Basically, if this triple appears in very few entity descriptions, which means this triple provides a lot of information because it occurs infrequently, then we will be more likely to jump to this triple because it provides more information. Well, this rally model can be easily extended because basically the iterative computation, in the iterative computation here we can actually combine more than two factors. We can combine an arbitrary number of factors. For example, in this extended work published at the WIME conference, the authors they extended our rally model by introducing a new factor called topic occurrence. I don't want to go to the details here, but I just want to say that, okay, here is an example of how to consider more than two features in this random sample model. You can have many features here. You just compute a linear combination. Well, so the strength of this random sample model is that it is very nature for combining centrality and importance style features. So, well, so recall that we computed a relatedness. Well, it's actually we want to compute. We want to find some central triples in an entity description. So it's actually kind of centrality style feature. And we also compute informativeness. Informativeness is actually a kind of importance. So, well, you can see the random sample model is very natural for combining these two types of features. But the downside is that the random sample model still, it cannot naturally represent diversity and coverage. So how can we, well, because diversity and coverage are known to be very important for summarization task. So we need some better models, some better frameworks. So now we move to the third type of framework. It's called similarity-based grouping. Grouping means that we divide all the triples into different groups. And this grouping is based on similarity. So basically, similar triples are put in the same group, so that we can generate a very diverse summary by choosing triples from different groups. That's a basic idea. So, so how can we compute the similarity between triples? How can we do the grouping? There are many different ways. So the most simple, the easiest way is probably to group triples by their properties. I mean, if two triples have the same property, so they describe the same aspect of an entity, then we just put them in the same group. Then we can prohibit the selection of triples having the same property. I mean, we can prohibit the selection of triples from the same group, so that the generated summary will be highly diversified, because all the selected triples are about different aspects of an entity. Well, but how can we choose the triple from a group? We of course we choose the top ranked one. We choose the top ranked triple from each group. Then we need to consider how we can rank triples within each group. Let's look at some examples. So this is also a very famous system called DiverSum. It explicitly considers diversity by choosing triples with different properties. And how this system ranks triples within each group? We rank triples by a property multiplicity. What is multiplicity? Multiplicity is basically the local frequency of a triple. So if, sorry, a local frequency of a property. If this property has multiple values for an entity, then this can be a very important property, so it will be more likely to be selected. In another system, they also disallow the selection of triples having the same property, but they rank triples in a group in a different way. They use RDA to rank property values. Well, this is grouping by property. Well, but you know that property is actually only a symbol. So if we group, it is possible that two properties are different. They are different properties, but they are actually very similar to each other. They are about the same topic. So we need to, so a better way is to consider the textual meaning of a property. So which means we can group triples by bag of words. This kind of framework has been used in two systems developed by Kappa. One is called Physis, published at AAA, and the other is an extended system called Physis E, published at ESWC. And so basic idea is that we group triples by bag of words model. So we collect words from a triple, from the property and from the property value. And then we, well, you know, a triple is a very short text containing only a few words. So basically, we need to extend the bag of words. We can extend the words by using WordNet. And so we can have more words, and then we do some clustering. We use the CopeWeb. It's a popular clustering algorithm for bag of words model. Then so now we have a grouping of triples based on bag of words. Then we select top ranked triples from as many clusters as possible. What does that mean? So it depends on how many clusters you have. For example, if we want to select k triples in the output, but we have less than k clusters or less than k groups. In this case, firstly, we need to select one triple from each group or each cluster, but still we have not collected k triples. In this case, we can select some other good triples from the groups that we have already selected from. But on the contrary, if we have more groups than k, then we can only select one triple from. We can select at most one triple from each group. So. Well, so for the WordNet-based extension, here is an example. So the original property is birthplace, and the value is a city. Then we extend the property using WordNet to get some upper level words like beginning, area, locality. And also for value, we use these types. We know that it's a city, it's a place, it's a populated place, blah, blah, blah. Yeah, so we have an expanded bag of words, then we do clustering. And for ranking the triples inside a group or a cluster, we can rank them by two features. First is self-information. We just compute the self-information of a triple. And then we also consider the property of the value. That is how many times this value appears in the entire knowledge graph. That is grouping by bag of words. So, well, there can be some other ways of similarity-based grouping, but the strength of these frameworks is that, well, clearly diversity and coverage can be have been explicitly represented because we try to choose triples from different groups, but this kind of frameworks is not flexible. Why? So recall that we have a grouping of triples. What is a grouping? A grouping is actually a partition. Okay, so we after we compute the similarity between triples, we partition the triples. So the similarity score is transformed into a binary score. So two triples are either similar, so they will be put in the same group, or they are not similar, so they will be put in different groups. So this binary similarity score is not flexible. As we will see later in the next, we can have some more flexible way of using the similarity score, which is based on MMR. So MMR is another framework. What is the MMR? MMR is the maximum marginal relevance. It is a very, very popular re-ranking framework that has been widely used in information retrieval research. I think the paper was published at 1998 CIR, and the same idea has been applied to entity summarization in another CIR paper published at 2012. So the basic idea is that we select the triples in an iterative manner. So we select one triple in each iteration, and in each iteration, we do a dynamic re-ranking of the remaining candidate triples. Why we need to do re-ranking? We do re-ranking because we want to improve the diversity of the generated summary. So the idea is that in the re-ranking, we consider not only query relevance, so here the summaries are generated to show the query relevance of an entity, okay? So we need to consider not only query relevance, but also diversity. So how can we consider diversity? So let's look at this formula. And so the first part, this similarity is a similarity between a triple and the query. So this is query relevance. But the second part is we minus. We minus what? We minus the similarity between the candidate triple and the triples that have been already selected into the summary. I mean, these triples were selected in previous iterations. So by minus this similarity, we actually improve the diversity of the selected triples. So this is called MMR, like re-ranking. It's very simple but effective framework. Is it good? It's good. It can flexibly employ numerical similarity. You can see here what the similarity is not used as a binary score to partition triples. We can fully exploit the numerical similarity score here because the score is directly used in the re-ranking step. So it sounds better than grouping. Well, but still, this framework has some shortcomings because, well, it has a greedy essence. It has a greedy nature. Well, clearly, it's a greedy algorithm. So possibly that it will not generate an optimum solution. But the problem is that what is the underlying objective function? So if we know that MMR is actually a greedy solution, so the best way is that we can try to find out the underlying objective function, and then we directly formulate a combinatorial optimization problem, and then we can, for example, compute an exact optimum solution to that problem. Then probably we will get some better results than MMR. Can we do that? Sure. So we move to the next frameworks based on combinatorial optimization. So this work, we look at a simple combinatorial optimization problem. Here is called quadratic knapsack. This system is called CD. It was actually developed by one of my students in 2016 in a workshop. This quadratic knapsack. So let's review what is knapsack. Knapsack is actually a bag. You have a bag which has a capacity, and you want to select as many as many items as possible and put them in the bag. Well, but clearly an item has a weight. The total weight of the selected items can't exceed the capacity of the knapsack, right? This is a constraint. But on the other hand, different items may have different values. So your objective function is to maximize the total value of the selected items. That's knapsack. So what is quadratic knapsack? Quadratic knapsack is a special kind of knapsack that not only each item has a value, but also every pair of items has an additional bonus. So let's look at the objective function here. We want to maximize this function. What is this function? So here P is profit or the value of selecting two items xi and xj. Xi is a series of binary variables, meaning that if xi equals 1, then the item I is selected. If xi is 0, then item I is not selected. So here is a constraint. Sigma means that we can't select more than k items. So the key point here is actually how to define this profit. Okay, how to define the value of selecting two triples. So when I equals j, which means that we are not considering two different triples, we are considering the same triple. Okay, so we are considering one single triple. So if this single triple is selected, the profit is itself information. So we tend to select informative triples. But on the other hand, if I and j are not equal, which means we are considering a pair of different triples, we want to actually, here is a minus here, so we are actually minimizing the overlap between the two triples, which means we want to minimize the overlap between triples selected into a summary. In this way, we can improve the diversity of the summary. Okay? And so now we will just skip the rest of the details. Well, so for computing, how can we compute the overlap between two triples? We can compute their ontological similarity. For example, there can be some subclass or subproperty redundancy. We can also compute a string similarity by using some edit distance or some other metrics. We can also compute a numerical similarity. I mean, if two property values are numbers, we don't need to compute the similarity between numbers as strings. We can directly compute some numerical similarity, so on and so forth. Well, this framework can be extended. How can we do the extension? So we consider a new application here. So the application is that we want to compare two entities. We want to compare two entities. For example, when we do entity matching, when we want to involve human users in this task, so we ask human user to compare two entities, whether these two person entities actually refer to the same real-world person, whether or not. We need to help users compare two entities so we can extend this quadratic knapsack problem. So our extension is that we redefine or we extend the profit function P here. So we need to, because now we have two entities, not just one single entity. So we need to consider inter-entity similarity and inter-entity dissimilarity, because we don't know whether these two entities refer to the same real-world entity. So we need to show their similar features and also show their different features. So we can compute some inter-entity commonness and inter-entity conflicts. So I don't want to go to the details here. Well, but the basic idea is that firstly we need to align properties, right? We need to find out whether these two properties in two different triples are comparable to each other. If they are comparable, I mean, if they're equivalent or at least similar properties, then we compare their values. Well, so for some properties, they're not very useful because, for example, if two people have the same gender, what does it mean? It means almost nothing. Okay, we can't conclude from this fact that the two people are the same person. No, they only have the same gender. It's a very weak connection. So we compute this kind of property distinguishing abilities. And we also want to show the conflicts between triples. So what if these two entities are different? We need to show how they are different to each other. So we want to show their different values of the same property. Okay. Well, we can further extend this framework. We can consider not only quadratic but also multidimensional knapsack. What is a multidimensional? So we look at a new application. The application here is that we want to compare more than two entities. For example, we want to compare 3 or even more entities, and the comparison has a context. The context could be a text. So these entities can be some entities mentioned in the text. So the text becomes the context for the comparison. Because we want to compare multiple entities, and we want to select at most the key triples for each entity. So we need to define multiple constraints, one constraint for each entity. Okay, so we extend the constraint to select at most the key triples for each entity. And the objective function is also extended because now we need to compare multiple entities. So I don't really want to go to details here. If you're interested, you can read the paper. It's actually a paper that we published at WWW 2015. And in a later work, Karpa and I also had a similar idea for a different application where we do not want to compare multiple entities. Instead, we want to relate multiple entities. I mean, here we can generate summaries for a set of entities that are mentioned in news content in order to explain the underlying connections between these mentioned entities. So we want to show their connections in a knowledge graph. So in the objective function, we do not show their conflicts or similarity, we show their relatedness or connections. So in order to show their relatedness, how we can compute the relatedness? We can compute their bag of words basis similarity. We can also use RDF2WAC, which is a method for graph embedding. So we compute their embedding basis similarity. Okay, so I will just skip the details to let you know that we can do knapsack in many different ways. Finally, let us look at learning to rank. So far, all the frameworks we have discussed are all unsupervised because it is expensive to generate labeled summaries for training. But what if we have labeled summaries? Then we can do learning to rank. Okay. So for some applications, labeled summaries are easy to obtain. For example, for an information retrieval task, we can use user feedback. We can use click-through data. So we have some labeled data for training. So we have seen these learning to rank models that have been already used in the literature, such as disease tree, linear regression, SVM, GT boosting. And we will particularly discuss some deep neural networks. Well, before that, the strength of the learning rank is that the feature combination is done automatically. We don't need any particular framework. We will net these models to decide how to combine features. But the shortcoming is that we need labeled data. Okay, let's look at two neural networks for entity summarization. The first is called ESA. It was just published last year at a workshop. So the idea is that we firstly we encode each triple, and then we encode the entire set of triples in the entity description to be summarized, and finally we generate a ranking score for each triple. So how do we encode the triple? So in the triple we have a property and we have a value. So for the property, ESA uses word embedding, and for the value they use the trans-E. Trans-E is an embedding method based on graph structure, and then we can concatenate the property embedding and the value embedding. So now we have a triple encoding here. We have encoded each triple in this way. And for a set of triples in the description of the entity, we can feed this set of encodings into, for example, a bidirectional LSTM to encode this set. And we take the output. The output can be fed into an attention layer. So the attention is supervised. It uses the gold standard, the ground truth summaries for attention. And finally, after a softmax layer, we output the ranking score of each triple. Well, so this is probably, ESA is probably one of the earliest effort of using deep neural networks for entity summarization. And in a later work, DeepLens is a recent work published at Deep Learning for Knowledge Graph workshop at ESWC. It's developed by our group, by Qingxia and myself. We also have these 3 stages: triple encoding, triple set encoding, and triple ranking, but we do it differently, different from ESA. So I will just highlight the 2 modifications here. First is that we do not use graph embedding. We only use word embedding. Why? Because we find that for the entity summarization task, graph structure seems not very useful. Word embeddings are very important. So for both properties and values, we use word embedding. And after encoding each single triple here, we do not use bidirectional LSTM, because LSTM is actually frequently used to encode a sequence of things, a sequence of items, a sequence of triples, which means that we need to decide how we order the triples. But triples are in a set. There is no natural order for a set. So if we consider the output of ESA, the output of ESV will be, the performance will be sensitive to the order we choose for the triples. We don't want to choose an order. We want to have an order insensitive result. So we use a different model. We use MMRP. And for the output of the MMRP, we compute the sum over all the triples. So the result will not be dependent on the order of the input triples, which is good. Well, I will just skip the rest of the model. So I think so far, we have seen a lot of different ways to combine multiple features. And in the next part, we will look at how this algorithm perform in practice. So we will see how we do the evaluation, and also we will look at some recent benchmark results. Okay, so let's look at how to do the evaluation. There are basically 2 types of evaluation methods for an entity for a summarization system. We can do intrinsic evaluation. We can also do extrinsic evaluation. What is intrinsic? Intrinsic summarization means that basically we invite some human experts to create some ground truth summaries. Then we just compare a computed summary with a ground truth summary. If the 2 summaries are similar to each other, then we can say that, okay, the computed summary is good. So this kind of evaluation has been widely used for evaluating general purpose summarization, because it's usually easy to invite experts to create some general purpose entry summaries. And the strength of intrinsic evaluation is that the results can be easily reproduced, because once the ground truth summaries have been created, they are there. You can reuse for your own evaluation. So you can also reproduce others' results very easily. But the downside is that intrinsic evaluation does not directly measure the effectiveness of a summary, because well, we know that in order to know whether a summary is truly effective, we should use the summary in the target task, right? But here we do not use the summary. We do not use the summary. We only compare the summary with some ground truths. So this is kind of indirect evaluation. So there is also extrinsic evaluation. So it's completely the opposite. In extrinsic evaluation, we need some task. And we directly apply the summaries to this task. For example, to help human users to complete tasks more efficiently. And then we observe whether human efficiency is improved in such downstream tasks. So this kind of evaluation is usually for a task-specific summarization tasks. The good thing is that we can directly evaluate the effect of these summaries in this particular task. But the shortcoming is that the results are not easily reproducible because human users are involved. Well, so in the next, we'll only focus on intrinsic evaluation, because there are already many data sets there. So each data set provides a set of entity descriptions and their ground truth summaries created by human experts. But unfortunately, some datasets are already not available at all anymore, but some are still downloadable. So basically, they use some. Most of these datasets use DBpedia entities, because DBpedia is a very popular, diverse knowledge graph. Some also use Freebase or LinkedIn, which is a movie database. In the next, we will only focus on ESBM, which is the most recent dataset that we published. So ESBM, for details, you can look at this ESWC paper. So basically, we sampled some entities from 2 datasets. We sampled 125 entities from the 5 largest classes in DBpedia, including agents, people and organizations, and also events, and also locations, species, and works. We also sampled 50 entities from the 2 largest classes in LinkedIn, including films and persons. So we imported their descriptions from datasets, and then we look at how many triples are there for each entity. So on average, in our dataset, each entity has 37 triples, which is not too much, and it's not too large and also not too small. But it depends on the class. For some classes, there are only 25 triples, but for some classes, an entity can be involved in more than 50 triples. So the number of triples is actually an indicator of the difficulty of the task. If there are many triples, the task is actually more difficult because you have more choices. We invited 30 researchers and students that are familiar with RDF to create ground truth summaries, because these knowledge graphs are in RDF format. So we need our human experts to be familiar with RDF, and we assigned to each participant 35 entities to invite them to create 2 summaries for each entity. One ground truth summary contains 5 triples and the other contains 10 triples. So we can evaluate in different 2 settings, one for 5 triples and the other for 10 triples. And so for each entity, we have 6 ground truth summaries from different experts, which is important because people usually have different opinions about what is a good summary. So it is very important to have multiple ground truth summaries from different human experts. And so in total, we collected 2,100 ground truth summaries, and we specified how to split them into training, validation, test sets, so that if you are going to use this data set for your supervised machine learning approach, in order for the results of different systems to be comparable to each other, basically everybody should follow this provided split. Here is an interface that was used by the participants to create a ground truth summaries. Well, because these entities are selected from different classes, you can expect that these entities have quite different properties. So as you can see in this table, we will compute the Jakarta similarity between the property sets describing different classes of entities. Clearly, the similarity is very, very low. So these entities are different from each other, which is good, because by evaluating a system on different classes of entities, we can test the generalizability of a system. Okay. And we also find that, well, so people have very different opinions, because if we look at the ground truth summaries, and we can see that only usually one or two properties are popular in more than half of the ground truth summaries, which means, you know, in the top 5 summary, there are 5 triples, but only 2 of them only 2 properties are widely accepted by most human experts. So people have different opinions. Well, so actually we measured the inter-rater agreement between human participants, and if we consider top 5 triples, so for 2 ground truth summaries, their overlap is approximately 2 triples. So out of 5 triples, 2 triples are the same, considered by different human experts. If we consider top 10 triples, then about 5 triples, about half of the triples are the same. So for the evaluation metrics, we just follow the popular information retrieval metrics, that is precision, recall, and the F measure. So we compare a machine computer summary with a human-made ground truth summary by computing the F score. And we tested 9 unsupervised systems and also 2 deep learning-based systems. There is also an oracle. An oracle is not a real system. In this oracle, we just select top-ranked triples that have been selected into the most ground truth summaries. So it represents a kind of upper bound for the performance of a system. And we do so for some unsupervised systems, they have parameters that need to be tuned. And for supervised systems, clearly they have some hyper parameters to be tuned based on the validation set. And we did a tuning very carefully. And here are the results. So clearly deep learns, which is a deep learning based supervised system, it very easily beat all the other systems, and it outperformed all the other systems significantly. But still, the gap between this winner and the oracle, the gap is very, very large. Okay, so which means the problem entity summarization has not been perfectly solved. We still need much more work to do in the future. Well, if we only look at the unsupervised methods, bar freak is generally the winner. It performed at least as good as all the other unsupervised systems. But actually, there's no single winner. I mean, if we look at different classes, there is no single winner. For example, bar freak is here, the purple one. Bar freak is generally the best one, but it is good on event, on location classes, on work entities, and on film entities, but it's not good on agent, for example. So there's no single winner across all the entities. So here is our evaluation results. And so I've done my part, and in the next my friend Evgeny will show how to continue to improve the summary, because as we can see in the evaluation results, the summaries are the current summaries are not perfect. So how can we improve the summaries? We can do it by leveraging user feedback. So we'll move to, we'll invite Evgeny to come back to talk about entity summarization with user feedback.
Thank you, Gong. Okay, let's move to the fifth part of this tutorial, entity summarization with users' feedback. Let's start with limitations. Limitations of existing methods. On the one hand, entity summaries are end-user oriented by nature, and you can see on this particular summary of Southern publications, it is done by Google and it is for end users. On the other hand, entity summarizers are often user agnostic. What they look at are, for example, generic features or specific features. This is what Kalpa showed you in many details. So those summarizers focus on frequencies, on diversities, and so on, but they're not focusing on a particular user. And as was shown by Gong, the previous part of the tutorial, it is often the case that summaries do not meet users' expectations. If we compare summaries constructed by machines and summaries constructed by users, then their correlations are not so high. The F measure is below 0.6 and in many cases much lower. Moreover, the summaries are static. They cannot adjust to users. Users cannot communicate anything to the summaries. So despite the fact that some of them take personalization into account, the staticness is still not addressed in this personalization thing. In our recent work, we proposed an approach where we allow users to actively participate in summary construction. This work has been published at ESWC 2020, and we will soon present it at this conference. You're all welcome to join our talk. Our proposal is to allow both the summarizer and the user to actively participate in the summarization process. So this is the old approach, where the summarizer is alone by computing the summary. Now, we allow users to provide feedback to the summary. For example, the feedback can be provided by some communication channel when the user tells to the summarizer that we either like, that he either likes or dislikes particular property value pairs in the summary. And then the summarizer utilizes this feedback and we compute the summary. There are two challenges in this approach. The first one is how to formalize this cooperative process of two agents. And the second challenge is how to combine results of actions of those two agents, how to represent interdependencies between the summaries and the feedback. Our solution for the cooperation process is to rely on a cross-replace scenario. In this scenario, the summary is enhanced with the delete button, where the user is allowed to dislike, to delete some of the provided and property value pairs, and then the system recomputes the summary and provides a new one. Let's look at the example in more details. For example, in the source of publication, the user may cross off the label source of publications. She doesn't like it. And then the system replaces it with a new property value pair found in here 1986. The user can continue and cross off another property value pair, subject United States themed superheroes. And the system will replace it with the new property value pair, industry comics. So we see that we go from summary S0 by deleting D0 and replacing it with R0. that give us a new summary S1, which can be further improved by replacing D1 with R1. At each next step only depends on the previous one, so it's a Markov process. And we formalize the whole thing as the Markov decision process, where the state of the process is a quadruple, capital SI, that consists of the current summary, capital DI, that consists of all the property value pairs that were crossed by the user in the previous interactions with the system. Capital CI is the set of candidate property value pairs for the replacement, and DI is what has been crossed out by the user. So here it is. We have this SI, the current summary, CI, the set of candidates, DI, what is crossed out, and then RI, this industry comics, is what goes up in there. Then the initial state of the process is when there is a summary S0, the initial summary, empty set of disliked or crossed off elements by the user. The candidates are essentially all elements in the description of E except for those which are already in the summary, and then there is some D0 disliked by the user. The action is RI, and the transition is application of the replacement to the current state. So this is the way that we address the challenge C1 cooperative process of the summarizer and the user. Then the next question is, how does the summarizer understands which RI to pick and put instead of the one deleted by the user? And this is actually the tricky part. This is the core of our novel proposal. Here, the summarizer is actually smart enough to look at what has been disliked by the user, then re-rank candidates, pick the one which is the most appropriate, and then ship to the place where one pair was deleted. And actually, by doing so, some of the property value pairs can be penalized and go down in their ranking. For example, name source and publications get penalized when the label source and publications was disliked by the user, and industry comics was promoted up and then used for the replacement. This policy is what addresses the second challenge, combining results of actions of the summarizer and the user. Now I will give you more details on how this policy works, and actually it is implemented with a deep neural network, and that's the reason why we called the whole approach as dressed deep reinforcement entity summarization with users' feedback. Let's look at the neural network. So the policy, this one, is essentially a softmax function that maps scores of candidates into a probabilistic distribution. At the same time, the scores are computed with a theta-parameterized neural network down there. So there are several layers in this network. The lower layer is the one that encodes individual triples, triples in the candidate, in the set of candidates, and also triples participating in the state. So in the first step, every candidate becomes an element of the vector space, it's encoded, and then every triple occurring in either the summary of the state or the deleted elements or the current candidates gets encoded. Then the second layer does triple set encodings. Basically, it takes the encoding of individual elements of the state and combine them into one vector. So that gives us this layer of vectors representing triple sets. Afterwards, network concatenates them into one representation and uses it to combine with every single individual element of the candidate triple set. By doing so, The system encodes triple interdependencies and scores candidates for the replacement. Then at the upper level, there is the selection of the candidate for the replacement. This is how this network works. We evaluated this network in against several baselines. Since there are no off-the-shelf entity summarizers with user feedback, we had to adapt a few summarizers. We took an entity summarizer faces E and adapted it for our case, for our scenario. Then we took an interactive document summarizer, IPS, which relies on user feedback to recompute document summaries. We also looked at a couple of interactive document retrieval systems that re-rank retrieved documents based on users' feedback. We look at ANRF, which is the one that takes negative feedback into account, and also PDGD that is based on positive feedback. And actually, it is actually state-of-the-art online ranking learning system. So we took those systems and we did two types of study. First, online study with users, where 24 participants participated and they did 840 sessions. We trained our network on entity summarization benchmark and tested on resampled entities from DBpedia and linked MDB. So the results are actually they're quite good. Dressed is in general best performing, with faces E, it is quite comparable in the number of iterations users did before they stopped. It's less than 4. And both of them obtain reasonably good results at the Q-stop. Q-stop is the user rating on the final summary after all the iterations. So the users rated summaries from 1 to 5, and both faces E and Dressed provide quite good quality summaries. On the other hand, our system Dressed performed much better in the replacement scenario. In this matrix Q RPLC, this one, where users rate the suggestions for the replacement that the system provides. In this case, our Dressed did a much better job than other two systems, significantly better job. We also conducted an offline study where for the benchmark, we used this entity summarization benchmark with some variations and FED as well. For the metrics, we looked at normalized discounted cumulative F1 measure, this NDCF for summary sequences, and the gain NDCG for the replacement sequences. As you could see, Dressed is in general gives much better performing than other systems. It outperforms all the baselines on all data sets, and in most of the cases, significantly outperforms them. Okay, that was all about the entity summarization approach with user feedback. Now we move to the last part, part 6, where I'll conclude and discuss future directions. There is a number of exciting future directions. One of them is the use of semantics. One could look at the ways how to combine ontologies with knowledge graphs and enhance summarization by relying on those ontologies. Reasoning capabilities could be of great help in these smart summaries. Another direction is human factor. As we discussed before, generic features and specific features which are not that much user-oriented are commonly used for summarization, but user-oriented features like meaningfulness, human friendliness, and so on, they can also be taken into account when doing entity summaries. And bringing all these features in one landscape, we think it has a great potential. Another direction is to enhance machine and deep learning methods for entity summarization that would require new methods for programmatic generation of labeled summaries for training. Another nice direction is about non-extractive methods. Methods that focus on abstractive summaries, like textual entity summaries. Finally, we gave a glimpse on how interactive models could be used to bring both algorithms and people together in computing good summaries. And here one can look at directions of relying on techniques from interactive IR or online learning to rank. They all have great potential to contribute into entity summarization techniques. We have a number of references, which you can see here, and we think that these are great papers, and we recommend you to read them to learn more about this exciting topic. There are more references, you can see them on the slides. Okay, we reached the end of our journey, of the entity summarization journey. I hope you enjoyed it a lot. And if you have any further questions, please feel free to contact us. You can see our emails on the slide, and we truly hope that many of you will become evangelists of entity summarization research and will contribute a lot on that in the future. Thank you. Bye-bye.